Hello and welcome back to Calculus 2. This is the last lecture of Chapter 6. And Chapter 6 was on application of integration. We did all the rotations and we calculated areas, we calculated volume, we calculated surface area of revolution, and we calculated length of the curve. All of that is applied because you want to know the length of the road, you want to know the volume of the bottle or a cup, you want to know the surface area of these things. So all of those are directly applied problems in design and engineering, mechanical engineering, and so on. So the last lecture is this lecture on physical applications when we are going to talk about certain problems from physics. So we start with the notion of density and mass. And the mass is a little bit misunderstood. In US system, which is called the imperial system of units, we measure weight. We don't measure mass. We measure weight. Weight is given in pounds, and pound is actually a unit of force. So when you buy 3 pounds of bananas, what you actually pay for is you pay for the force that the bananas pushed against the scale. That's what you paid for, right? Because you bought 3 pounds, which is unit of force. Now, if you go to Europe and you pay for a kilogram of bananas, you actually paid 4 bananas because kilogram is the unit of mass. Now, mass, I like to explain, there's a lot of physics behind it, and they were looking for the God particle, which is the one that gives mass to objects. Yeah, Higgs boson, very good. So you can go and research those things. There is a very easy way to understand what mass is. Mass is a quantification of physical existence. What's not on that scale? Love, right? Love doesn't have mass. It does have force, right? But it doesn't have mass to it. So who has mass? Anything that is manifested in the physical reality that you can measure, right, in terms of grams, kilograms, and so on. Does anyone know what is the unit used in imperial system of units for mass? There is one. So pounds is force. What's mass? Slug. Very good. Slug. And slug is about 15 kilograms if I remember. And you would measure, yeah, slug. Look it up, right? That would be a unit of mass. But you know, when you take medication, it's 200 milligrams. It's going to be metric kilograms unit of mass, right? So kilogram is 1,000 grams. Milligram is a 1,000th of a gram, right? So you have 1,000 milligrams into a gram, and then you have 1,000 grams into a kilogram. So that's what you have. So now, mass would be the, as I said, quantification of physical existence. I can distinguish between the phone and the case, right? This one is more massive than this one. Now we do say heavier. Now, if you measure your weight and you stand on a scale, right? Let's say you are like me, 275 pounds. You sit on a scale, or sits on a scale, don't sit, stand on a scale. You stand on a scale, you measure 275 pounds. You see, the unit of force is equal to mass times acceleration. Now, force is the vector, and acceleration is a vector, because acceleration needs the distance. It's important which way you accelerate, right? You push the gas pedal to accelerate in one direction, meaning change your velocity up. You press the brakes, which is deceleration, to decrease the speed of your car. So both pedals that you have in a car are acceleration pedals. One accelerates, the other one decelerates. That's just the sign on the vector of acceleration, positive or negative. That's all it is. So those are your two pedals that you have, right? And then you hopefully You use your arms to turn the wheel rather than, like some people, knees. So now you have the force. So this means that if I am 275, that would be equal to my actual mass times the acceleration, when that acceleration is going to be acceleration of gravity. So, well, we can't use negative 9.8 because units, very good, right? You know how they programmed the Mars lander in one unit, they design in the other, and like, right? So, yeah, keep the units consistent, right? $1 billion, poof. Right? The same reason, you know, you have a nurse that can't convert units. What happens? Anyway, so we have to use 32.2 feet per second squared to plug in for gravity, and I would be able to calculate my mass in slugs, right? So, you know what? I'm not going to use 275 pounds for this calculation because, you know what? I don't want to use 270 pounds ever. Because if I stand on a scale on Earth and I measure my weight as 275, do I actually need to do any exercise? I don't know why people say, you know, if you lose weight, you're, no. Usually you're happier. Anyway, because it's more of you, right? If I take myself to the moon and measure my weight there, it will be significantly less, because the gravity of the moon is significantly less than the gravity of the Earth, and that's what goes in the equation to multiply. But see, if I measure my mass, and let's say I'm 120 kilos, well then, if I put the scale on the moon, I put the scale on the Mars, I put the scale anywhere, no matter what the gravity is, it is always going to say, step off the scale please, 120 kilos. Actually, no, Weeboard did tell me that. You're too fat to play. I'm not kidding. Their scale goes to 250, and then it's like 255, okay, we'll still let you play. It literally told me get off. I said, this is what happens when you have Japanese people, you know, do the design, right? They're not used to me. No, I'm serious. I have it at home. The We Fit. That's the... So if you have that issue or planning on having that issue in the future, it's easy. Just get cakes. I programmed myself. I made a new me. I sit on a couch, put my legs on the board. I weigh the legs only, and I register myself as a 4-year-old. I don't have to get up. The We Fit, right, the balance games and everything works great. I have all higher scores. My son is 4, he can't get anywhere close. Like, you see where your dad's score is? You loser, go, 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 right? So he's poor trying to, right? That's how you play Wii, right? But you need to know, you need to know physics, right? You need to know math, and you can do these kind of things. And it's not fair. I mean, they could have put more resilient springs in the thing. What? That's what happens when you lose. My score is top. He gets to be the winner when he beats that one. Right? So from now on, work on it, buddy. Earn, right? So this G has to be 32.2 feet per second squared. So now, mass. Mass, as I said, quantification of physical existence, is measured in grams, which is G, or kilograms, which is kg, which is equal to 1000 G. G is grams, not G is gravity. So get your letters straight. Now, We can calculate, and this is the first formula you are memorizing. If you don't know already, you should know. We are calculating mass as the integral of density, and we can use rho, Greek letter rho. So this rho of x is a density function. So this is our equation, and you can use this equation to calculate the mass of the object. Now, mass, density, and volume are also related. So if you took any of the chemistry or physics, rudimentary chemistry and physics courses, right? You can also find that another way to find mass would be density times volume, right? That's another way. But this formula is very interesting to us because what you are doing here is you are allowing for variable density. You have to make clear distinction between two different levels of physics. We teach them both here at the college. There is general physics. Only general physics 1 and 2 has no calculus in it. There are no derivatives, no integrals, and the equation that the mass is equal density times volume is the only equation that you get. And in that physics class, since you can't see integral, you can only deal with uniform density. So that means if you have a metal rod or you have something, it has to be made out of the same material throughout. You can't have the variable density inside at all. Now, this formula here with the integral allows for variation in density. So you can start with the object that is denser on one part of the object, and then be progressively less dense as you go through. Now, in the design, when you're designing things, uniform density of things that you design and variable densities play the key role, especially for what is known as the center of mass. We are only going to do the one-dimensional integral here because we are stuck in, two-dimensional integral, right? But it's only for length. So one-dimensional length, these would be the extremely long rod, just a long rod, would apply here. But when you go to Calc 3, you would be looking in third-dimensional space for center of mass. Do we have any mechanical engineers here? Are you going to work on cars, airplanes, and things like that? Right? Why is Tesla the safest car ever made in the galaxy so far? Why? Because there's no engine, there is no top weight for the car. The battery sits underneath you, and the motors are both on the front and there is no top weight. It's impossible to flip that car. Now, take an average SUV, right? If you drive anything like me, you're probably going to flip that car in the first 2 days. So, the problem that we are facing now is going to be upgraded to the 2 dimensions, because you can regard this as a 2-dimensional, because it's very thin, right? So third dimension can be ignored, right? Third dimension can be ignored because it's very thin. All I need to do is to find where the center of mass is and sit that center of mass on my finger, and this thing will be perfectly balanced, right? It won't fall off. Now, we can calculate that, right? We can calculate that, where that center of mass is, and yeah, I'm not a good juggler, but there you go. This is the time to applaud. You terrible, terrible people. Thank you very much. Now, I worked hard on it for 17 seconds. Now, wasted 2 calories. It's a unit of energy. So now, this one is going to be for long objects. Here I have a long object. So this object, right, if this was like a metal bar, right, I would be looking for a point somewhere that would make that. Look at that. On the printer right there. I just have to get up. A long time ago. Right here. All right. Look at that. It's called skill, right? So do we all agree that this is a three-dimensional object, right? You can try it if you want, right? No, I'm serious, you can do this. Now, we are going to ignore its three-dimensional presence in the world because this one dimension is much more visible and present than the other dimensions that are making the thickness of it. So I can regard this as a one-dimensional metal rod, and I can say, let me calculate the center of mass. Well, great. In order for me to balance this and calculate center of mass, I need to know what the mass of this thing is, right? Now, all those problems that I said, they're in concrete to calculate the center of mass. But now, at least, what I can do is I can think about density, which is the part of our equation. I hope we will all agree that this metal rod is denser on this interval than on this interval. Would we agree on that? Let me put this against my Rotaract banner and say one more time that it should be denser here than there. Oh, yeah. Why? Yeah. Oh, now you see the holes, right? Great. So this side is denser here. Then you have less dense, then more dense. So that's what is called variable density. Density is higher, density is lower, density is higher, density is lower, density is higher, density is lower on the equal intervals. Does that sound like any function? Higher, lower, higher, lower, higher, lower. Sine. Oh, look at you guys, right? So we can pick the data for the density here because that's what we measure in the lab. So I pick the density, and I snake the sine function through the points that I have in my data. And then I take that sine function and stick it in this integral, and I have 0 to, this is 4 feet, right? These lengths are 4 feet. Actually, these are shorter over here. No, that's the 4 feet. Yeah. So, so I know it goes 0 to 4, right? And I will have to do my sine in terms of again, imperial units, so feet and inches. And I plug, so see, by the way, what I just did, stuff for your project looks like that, all right? Stuff for your project looks like exactly what I just did. And you told me it was a sine function to model this problem. So you know how to do these things, right? You just need to put your brain to it, and that's your engineering, right? So I have the density function, and you can see that the density function is not uniform all the time. If this metal rod had no holes, it would be uniform density everywhere. And guess what? I don't need the integral. Just use the basic formula, right? Mass times the volume, you're done, right? But in this case, we have the variable density. Now you will see variable density everywhere. Clearly, for your cars that they drive, right? You have a dense engine block. There's not too much room in there. Would you all agree that there is much more room in a cabin where you sit, right, than in the engine part? Depending on what or who you have in the trunk, you will have variable density there, right? It's full or it's empty. Variable density. The amount of fuel in a tank. You see the variable density throughout the car. Now, the density of the fuel and the density of the metal and plastic and all of the other things that are part of your car, that's not the same either. There's a lot of headache for designs of such things. And then bring it one step up. Let's make an airplane, right? Now you have to worry about more things. So if you are considering these things, I understand that you see that printer over there as like a black box, that it's a solid piece, but it has variable density inside, right? Variable density inside because various moving parts, you have the rubber belts, you have the gears that are plastic, then you have the toner and metal pieces, you have the heat part that is metal and ceramic and all this, all different densities. So that printer is a variable density inside, right? And as mechanical engineers, you need to be able to compute that. So now we know that mass is the integral of density, and I'm going to jump immediately into the homework assignment and calculate one of these variable densities for something. Let's go with problem 20, I guess, because we can. So density function, rho of x, see you next week, is going to be x squared on the interval 0 less than equal than x less equal than 1, and x 2 minus x on no coughing 1 less than x less equal than 2. So now what's the mass? Well, we observe that, yeah, the integral should go from 0 to 2, but it has a different function in between. So what do we have to do? Split the integral, thank you. So common sense would be to say mass is equal to 0 to 1, x squared dx plus integral 1 to 2, x2 minus x dx. So we have to use two integrals because this particular object has variable density. I'm not sure if they still use the same technology for circuit breakers or not, but circuit breakers use the density of different materials to interrupt the circuit if the sensor, right, if the circuit breaker senses that the current is overdrawn, right, so to switch the, so what they do is they would take two metals and, yeah, and they would put them like this, and they have different densities and different specs, and then as you draw current through them, one will heat more than the other and it will bend and opens the circuit. Like, cool design, right? And then what the people do? Oh my God, my circuit breaker starts, constantly pops out. So let me take the 20 amp up and put like a 30 or 40 in, and then they worry why the house burned down. Yes. Yes.
Does it matter that one is not part of that function? It's created, right? It's not created.
We can draw this function on the interval 1 to 2, and we would know exactly what part it is, right? What do you mean 1 is not part of the function?
I mean, like,
I am able to plug 1 in. If 2 minus 1 is 1 times 1, which is 1. Good. Oh, that's just for math purposes, because this is a piecewise function, so you can't have equal if these functions are not joint at the point. So yeah, you would still use it 1 for the limit. Now I understand. So the question was, hold on, there's no equal sign on this 1. How come you put 1 over here? Put like 1.1 or something. No, we still put 1 there. So x cubed over 3, 0 to 1, plus, FOIL this, 2x minus x squared. So we have x squared minus x cubed over 3 computed from 1 to 2. So this is going to be 1/3 plus 4 minus 8/3 minus 1 plus 1/3. Great. It's going to be a negative, so this is going to be 3 minus 2. Answer is 1. Mass is 1 kilogram or 1 gram or 1 milligram or whatever you are working with. Cool? Well, we're done with the first part. That's the mass, the integral of density. You will have some kind of function, you integrate, and that's the first part. The next part, I already, oh no, I didn't talk about this yet. I did tell you the force, right, is the mass times the acceleration. But now we're going to talk about the work. So if you take the general physics, right, the non-calculus one, they will tell you that the work is equal to the force times distance. So you have to apply force over distance. Observe him, he's going to do it now. He's going to push the door through the distance. See that? That did the work. That took effort to open. No, I'm serious. That's what the work is. You move object from point A to point B, you cover the distance, and you had to push, right? Unless it's a horror movie or something, you look at it like Star Wars. Now, yes, use the force. So, contact between the object and the subject. And the work would be the amount of force which I push. Now that's a vector, right? So what can I do? I can do this, do that, right? The amount of force is different, so it differs in how much work has been done, right? The harder you push, more work has been done, which is completely opposite on how you compensate people, right? The harder they work, dig a ditch or something, they earn less money than those who push the pen, right? They make more money. It's inversely proportional there, but you do more work for less pay. Now, the angle of attack is important because if you take a look at the vector with which I am pushing the object, you see that the vector is coming in at the angle. All of the force that my legs are producing, channeling through the body, right, are going to push through this, through the arm. And the interesting thing is the position of the arm. If you look at the arm, right, it's coming in at the angle, and if you break this apart, you will see that there is a part that is going forward. That's the one that is pushing, but there is also a part that is pushing downward. That's wasted energy, right? Because as I push this way, some of the force is pushing into the ground, but I am not burying this into the ground, right? So if you try to push like this, right, some of the work is wasted. Now, let's say this is extremely heavy, right? You would see people push like this, and it blows. You push like this, it won't work. Why? Well, now when you push like that, look at the angle of attack. If the angle of attack is the parallel to the surface, all of your push is translated to work. There is no waste in force. Because when I do this, I am burying. Now, I don't really want to rip carpets here in the room, but it's a good exercise, right, to try to push this desk. It's not easy to... So this desk is not, I mean, I'm infinitely strong, so for me it's nothing, but if you try, right? You push this way, you will start ripping the carpet. Because you are leaning onto the desk, and some of the force that you are applying is going to be trying to bury these legs that you have, and those are metal legs, right into the carpet, ripping the carpet. However, if you go like that, it's going to be, that was zero effort, right? Because you are parallel to the surface. So when you know physics like that, right, the hard labor becomes easier labor, right? That's one of the things. So that's why you try to, learn as much as possible to be as lazy as possible. And all of this applies unless you go to the gym. You go to the gym, everything you pick up is very heavy, so just don't go. It's no reason. So now, what happens with the push? Let's say you have to push a fridge, right? Do you, as a human, get to push the fridge with a constant force? No! Because you lean to the fridge to push, you're still not pushing, the force is zero. As you apply, the force gradually goes up as you push, and then let's say flattens out as you push, and then you go the distance and you start getting tired. The force starts going down of your push. You're moving it now slower, right? Because you're covering less distance, because less work has been done, because you're getting tired. So if you are pushing, so I'm just going to draw the force graph over here. This is F, and it's like that, flat, boom. Force over time. Now, human push. So, in this case, you just touch the fridge. You just touch the fridge. You are not pushing it yet. You go into your display of power, right? The force goes up, and then you start getting tired over time, and then you quit and call professionals. Now, is this uniform? In the case like this, if you really want to represent what is happening when you push the fridge or piano, whatever, you will have this thing that it's not uniform. So now we need a better formula than the one in non-calculus physics. This is where analytical physics kicks in, right? And we define work as the integral of force times dx, which is the distance, and that dx is a to b, which is the distance that you're covering. In this case, let's say a to b on the force graph right there. So this is the formula that you need for this section. Work done when you have variable force. So let's think of an example, right? Say your force is given as would x minus x squared work? If the force is given this way, this is your f of x, variable force. What do we have here? One of the intercepts, if you factor out x, you get x minus 1 minus x equals 0, x is equal to 1, so 0 and 1. So this is a downward opening parabola, 0 and 1 for the force. And you clearly see what happened. You touch the object, you start pushing, investing the force. When your force peaks out on the top, you start getting tired right away, right? And then, right, it goes down. This is what happens when you do an exercise. So, can we calculate the work? The answer is sure. How much work is done from, let's say, 0 to 1? So, work would simply be the integral 0 to 1 of x minus x squared dx, and you just compute this. So that's x squared over 2 minus x cubed over 3 from 0 to 1. So that's 1/2 minus 1/3, which is 1 over 6 and the amount of work is 1/6. This could be in joules, could be in calories, could be, right, depending on what you are computing. Now, Newton meters, calories and say units of energy. Newton meters, which is force times the distance, or you know this is a foot-pound in your system that we use here. So it's either foot-pound or it's Newton meters, depending on which system of units. So FTLB or Newton meter, NM, depending which one you want. Great. So now we know the way to compute the force, they like problems with springs because spring has non-uniform force. It's like a rubber band. It's always in opposition. You compress the spring, it wants to go out. You stretch the spring, it wants to go in, right? It's like our political campaigns. And then rubber band does the same thing. So now, the more you stretch, the more it wants to oppose. The less you stretch, it wants to oppose less. So clearly, it's non-uniform force. As a kid, right, you maybe made those, what I call when you like scale an object. Not a bow and arrow. Slingshot? Slingshot, thank you. Yeah, you go, you cut a branch like Y, and you just put the rubber bands, and it's like, right? That's something that I could just make for my son, and then see if he can hit the target. He's probably gonna miss all of the shots and then sneak it into the school when I'm not watching and hit the target on the first shot, which is terrible, but that's how it goes. You know, they say the stray bullet never misses. Unfortunately, right? So we're looking into a spring, and you have, there we go, spring attached to some crate over here that you want to move with the spring. That's one big spring, if that's a crate, that it's 6 feet tall. So what's happening with spring? Well, first we have a law that tells us what the force of the spring is in connection to the stiffness of the spring, which is known as a spring constant. So spring constant K measures stiffness of the spring. So if you take a look at the spring that is in your pen, which you click, and you take a look at the spring from the shock absorber from your car, let's say, or pick a train, it's even more fun. You can't even lift those. I can. If you compare the two springs, they look the same. One is bigger than the other, one is thicker than the other, but they both look the same as a coil, right? One you can do this with, right? And the other one you need a Superman to do that with it, right? Still possible, right? So now, what is the difference between two springs? You might say, well, this one is bigger, this one is thicker, and so on. K, very simple. K is the only difference between the two springs. They conceptually look the same. It's just a coil that goes up. They both compress, they both stretch. You need much more force to stretch or compress the one that is on a train shock absorber, right? Absorber, can't say the word, than the one that you have in your pen, and you go click. And then when you add the lead, you just throw the pen away. It has a spring in it, right? You can build some mechanical things with it. So that's the spring constant. And now we use that in Hooke's law, where we say that the force is equal to negative K times delta X. Now delta X is the amount of stretch. Could also be compression or compression. Why is it negative? Because it's always in opposition, right? You stretch the spring, it wants to shrink. You shrink the, right? You compress the spring, it wants to stretch on its own. So now we have a formula that gives us our f of x, and we see that it depends on the spring constant k, and it depends on the amount of stretch or shrink, right? And now we get to plug this in, our work integral. So I'm going to call this work done by spring, Ws, and it's still the same formula. But now we know what f of x is, right? It's going to be given for spring. It's going to be given by the formula up there. That's better. It takes 30 newtons of force to compress spring 0.2 meters. Find K, spring constant. Okay, well, we know that the force is equal to negative spring constant times delta x, which is negative, which is force is 30 equals to, on the other side, negative k times 0.2. So now, k is equal to, and you can write over here, negative 30 over 1 times, divided by 0.2, so that's times 10 over 2, like this, which is equal to 5, so negative 150. We'll still use the positive number, but we need the negative for actual calculations. So it's going to be 150, so constant k, you can ignore negative just to present k, but you would use negative in calculations as you move on, because remember, physics is also about which way you go, not just how fast. Right? You see speed limit on a highway because they're assuming you will be going the same direction as everyone else. There's no need to say velocity limit, because velocity is the one that assumes how fast you're going and a direction in which you're going. So you will just say 150, and the units for this would be Newton divided by a meter. Yes?
So that negative is saying that it's compressing?
That it's opposing. That's all it says. It's opposing.
Okay.
So you stretch a spring, it wants to compress. You compress the spring, it wants on its own to stretch.
Okay.
Right? So it's just telling you about the opposing motion. So now we go and say, great. So now we can calculate work done by the spring. Since we know K, we can calculate work done by spring to compress or to stretch the spring from one place to another. So let's say you have a spring, and when spring is relaxed, that means spring is at equilibrium, and that's its natural state. All objects in nature tend to be in the lowest energy state. That's why vast majority of people are lazy, because it's the least amount of energy, right, displayed. Vast majority of people is lazy. That's why the planet is round, like a ball, because each particle of the planet, I'm talking atomic level, and I'm talking all of the rocks and all of the lava and all of the water and everything, is trying to be as close as possible to the center. And the only way to arrange that is if you have a ball. That's why all of the planets and satellites and everything, like the moon and so on, they're all balls, including the sun and stars, right? You're not going to go there and find a planet in the shape of a banana, because it will be a lot of effort for particles to arrange in that shape. So now when you have a spring, its natural state is to be relaxed, is to be at zero, which we will call equilibrium. Now you are going to disturb the system by stretching it. So now you say you are going to stretch this spring to 0.3 meter mark. How much energy is used to stretch the spring 0.3 meters? So what do we have? Well, we have the integral from 0 to 0.3, because we are pulling the object, the distance that we are covering, right? The dx is going to go from 0 to 0.3. We are stretching the spring, right? So we are pouring the energy into the system. Remember, spring was happy, right? It's not going to move anywhere unless you disturb it by adding energy to that system, which is compress it or stretch it. So now, what do I have? My force is the force of the motion. So that's going to be my kx. That's this formula here. Let me go orange for that. Remember that we're going to plug in negative 150 later, so don't worry about the negative now. So that's your force, and then you have your dx at the end. So what we have is the integral of negative 150x dx from 0 to 0.3. It's more of understanding what you're doing in physics world rather than actually, you can all integrate this in your sleep. Half of 150 is 75, so negative 75x squared from 0 to 0.3, and we get negative 75 0.3 squared, which is negative 75 times 0.09. Can we just call this 0.09.1? And the answer is yes, we can if you want to. So we're just going to have negative 7.5. It's engineering. It's just everything is, yeah, everything is rounded anyway. So it's about negative 7.5. Negative 7.5. What do you mean negative 7.5? Why is it negative? We are saying that the work is negative. Yes, the work done by the spring. The what? Is the spring pushing, or the spring is being pulled? This is from the frame of reference of the spring. So you have to think about the frame of reference of what we're talking about. And this is work of a spring, not your work, right? So you have negative 7.5 Newton meters for work presented. How about if you compress the spring? So your spring was happy at 0, and then you came along and said, you push it to negative 0.2. Same calculation. We just have to worry about the limits. So integral of what? Now that is a very tricky thing. It's 0 on the bottom because your spring starts at 0, okay? And then it's going to go to negative 0.2 because it's going the opposite way. So this is where your grade dies if this shows up, right? Or putting these limits up. Because you always want to put the smaller number on the bottom and the larger number on top, right? Because that's how integral works. But then don't you remember that you had a theorem in Calc 1, I think it was 5.4 or whatever, that they teach you that if you need to swap, you get to put the minus in front of the integral? You know what that minus is going to do? It's going to kill the minus that you have here. It's going to kill this minus, right? Yeah, it will. Obviously, if you're going the opposite way, the work has to go on the other end, right? Because now you're pushing the spring, you're compressing, is the positive work done. So you can't have stretch of a spring and compression of a spring to have the same sign on work. That would not, right? Because it's not the same to push or to pull, to stretch or to compress. It's the opposite physics. Mathematically, we don't care. We can just say, yeah, work done was 7, right? Whatever. But in physics, you really need to be careful because, again, in the design of a car, you have acceleration that increases your velocity, and you have deceleration, which decreases your velocity. They are both acceleration pedals. They're just with a negative sign. Your brake has a negative A affix, and your acceleration pedal, gas pedal, has A, positive A. Yes?
Is the calculation like similar to magnetic force?
They're all the same. Yeah. All of them. So you can work out the force in the gravitational field or the attraction between two objects. You can calculate the magnetic field work done by, yeah, the electrical engineer sits right there, right? He's going to be calculating this in the electromotor, right? Well, you have the rotational field, so you give the next class, but for that one. But the work being done over here, right, in the compression versus the pull, one is going to have minus sign, the other one is not. So be careful about that stuff. And I hope, one more time, that you understand why these limits are like that. The first one, let's go on top again and talk about this one. The spring is happy at 0, and you are the bully who pulls it out. So your integral is going to start at 0, and then because you stretched at 0.3, it moves to 0.3. In a second example, the spring is happy at 0, so your integral starts at 0 because that's the first moment in our reference frame, right, in development of things. If you record a movie of this, the first thing that happens is spring is happy at 0. And then you, the bully, right, and you compress it to -2. So this is like a time frame. This happened first, spring was there, then this happened next, spring was there. And then swap those, put the minus here using the theorem from Calc 1. That's -150x. Calculate the same stuff, and you will have positive value this time around. You mean calculate?
Yeah.
Sure. So the next step over here would be to say -0.2 to 0 with a negative in here, -150 x dx, and you negative and negative die off, so we have 75x squared calculated from 0.2 to 0. Then I plug in 0. Hold on, I'm getting a negative number here. That -15?
Should it be from -0?
When you square it, it kills the negative. It doesn't matter.
Still negative.
Oh, right, yeah.
Wait, where's my mistake?
Oh, yeah.
What?
It's yours on the block.
No, but that's why I have this negative when I switched it.
Why is your
When you square your 2, you get a positive.
Yes, but when I plug in 0 for x squared, I get 0 first, and then minus. Now when I square it, I get the positive. Oh, negative 4, well, still it's 0.4, so it's going to be 75 times 0.04. So what is this now? Oh, I doubled up on negatives in a setup. I had a negative inside the... Now I have to explain everything from scratch. Ah. Okay, so Hooke's law has the negative built in. So we put negative 150. So you either do that or you do these limits opposite. So the limits need to be, if you're going to use, well, no, they were good this way. But if you're using negative 150, then you have to flop the limits. If you're using positive 150, then you use these limits and the negative comes from there. So, yeah. It's positive work to compress the spring.
Can you say that again?
Yes, I'm going back to it right here. When I talked about the Hooke's law, right here, I told you about the negative sign. And the negative sign is there because the spring, the force on the spring always opposes the motion that the direction you push it in. So if you compress the spring, it wants to go out. If you stretch the spring, it wants to go in. So now, you can either use the negative there, or you can use the fact which one of these numbers comes in first on the integral. And what I did is I used the frame of reference of what's happening first and what's happening next to set up the integral, but I already used the opposite sign within k. So I doubled up on the negative, and it turned out to be negative at the end.
So you still use negative 150, but whether you flip the integral depends on the direction of the force.
Yeah, so maybe I should just say negative k and we leave this as negative 0.2.
So if we take negative k, then we always keep it like a smaller number at below and the higher number above.
Yes. Or you just use the positive. See, math doesn't care. Math doesn't care about the directions. Physics does. So from math perspective, you don't have to mess with the negative formula at all. Right? But physics doesn't like that. So there's never free lunch. Now, one type of a problem, which I don't think they discussed in this book at all. Oh, no, they do now. Oh, so this is what's new in a book. Nice. All right, let's talk about lifting things off of the floor. Clearly, if I am to drop this and I lift the entire thing, right, in one shot. So the amount of work that I do is just going to be how heavy, the mass of this, right, times gravity times how high I get it, right? And I'm going to put it to the ceiling, 10 feet up, 6 feet, right here, right, or 3 feet. So how high are you going to lift the object? And again, since you are lifting the entire object at once, right, you don't have any changes in anything. Therefore, you can use your basic formula from general physics and you are done. Let's say you are lifting a chain or a thick rope, which is coiled on the floor. Is that different than lifting this? Why is it different? You only lift the part. And what happens if you lift higher and higher and higher and higher? It gets heavier and harder, right? Because more links are added to the weight of the thing that you're lifting. Remember, entire chain is sitting on the floor, right? Right there. And then you pick up only 3 links, 10 links, 15, 20, 30 links, 40 links up. 40 links up, well, it's 40 links times the mass of each link. There are another 100 links to go. The more I lift, the heavier the chain. So now what happens with the mass? Mass is not constant anymore, right? The mass is changing, the mass is variable, and this is where the integral kicks in. Integral kicks in these types of problems. Anyone? Come on. Yeah, thanks. Because I want to sit here. So the chain or the rope, right, gets heavier and heavier and heavier and heavier. So you're lifting more mass, which means you have to put in more work. So you are using uniform work when you pick up entire object. You drop an apple, pick it up. You drop a book, pick it up, right? If you drop a chain, right, you can maybe pick up everything at once, but generally you start picking little by little, right, until you have everything. So the height to which you are lifting the object, whether it's a single object or the whole thing, is y. Therefore, these integrals are dy, because you are operating in the y direction, right, on the graph. So now, lifting problems. So for lifting problems, we're going to have, so let's go with simple first, simple. So when you have an object, here's a crate, right? And you just simply lift that crate. The work done is going to be force times the distance, right? So force is mass times gravity, and then times the y, so mgy, and that would be the work done to lift the object. Can anyone for $1 million tell me what is this formula for in your physics class? I think I heard it somewhere. Potential energy, very good. It's a potential energy equation. So I'm going to say over here you have your force and you have your distance, because you are lifting it up now. It's a dy. So that's the work done. And good enough. Now we want to complicate things because we want to lift the chain, let's say. So chain. Chain sits on a pile, and then we lift some of it up. So the distance that we are covering is y, and what is changing? The distance of how high you are going is changing, and what else is changing? The mass of the system, because you keep adding more mass to this. So you have two things that are growing in this particular system. So now we have to set up the integral for that. Now it's going to be a dy integral because we are lifting up, right? We like our y-axis to be up. So work is going to be integral. We can use C and D, right, for dy. And we know it's going to be dy. We also know that we are going to have gravity in this mix here, because the gravity is it's a constant. You can even kick it out of the integral if you want. Now, remember how mass is changing? How do we calculate changing mass? We did that first. It was the density function, right? Hello, rho, in this equation now. Hello, rho. We need to introduce the density, right? Because density will lead to mass. And we have a changing density, we have a changing mass. The more links you add, the more mass you have. And now we need a term that will discuss the height of the object. And for this particular term, we need to know how much of the chain we need to lift, right? At which point you are in your lift process. So we can say that the L is the length of the chain. So, length of the chain minus y. Now let's draw a diagram for this. So here is the chain. There's still some left on the pile. And this is how much the amount we lifted. Now, over here on a pile, there is the length of the chain minus the amount y that we lifted. Does that make any sense? Now, if I want to follow a particular point on the chain, going up as you lift the chain, right? That point will travel up as you lift the chain. They do give you the diagram in the book, which is cool. This is new. Your second edition and first edition book, they don't have this. This is completely new. Now, if you have a Larson book, they do have this. And I think it's the bulldozer that's lifting the chain. Over here, they have this man who's either lifting or is about to make another step. Yeah, it's the Apple boy. It's wrong, I know, but it's the truth. So observe this point here. This is the y at which that point is, and this is the entire 10 feet or 10 meters, the length of the chain. How small is this person? If this is in feet. It's not even a 4-year-old up there. Like, who let a 2-year-old up there? Still tall for meters. I'm 2 meters. Then it's a line. It's good. Anyway, it's wrong. So, and look at this. You have your density times gravity. All of the chain is going to be uniformly dense, so that's constant. And you're going to have the gravity, that's constant. And now you are observing a single point rising. And as you can see, at edge point here, it's at height y with 10 minus y left to go. So the entire, this is why I put on the pile of chain, they stretch the entire chain. In my case, the chain is still on the ground, so the amount to go is still L minus what's already lifted. So, if you observe this chain here, if you observe a point, a random point, right, that point is lifted y, there is 10 minus y to go. So you are measuring over here, you have the length of chain, which is 0 to 10, that's the distance to be covered. You are measuring how much you need to lift to cover the entire cord. Look at this. When you lift the entire chain, the y becomes 10. 10 minus 10 is 0, and at that point you can stop applying work because the chain is lifted. Would you agree? If you haven't lifted any of the chain yet, then the y is at 0 level, none of the chain is lifted, so 10 minus 0 is 10, you still have 10 feet of chain to lift, which would be all the work you have to do. Does this make sense in the formula at all when you look at it? So if you look at it that way, you say, okay, the length of the chain minus the distance I have to cover. And that's the work that needs to be done. Because Joe can lift 4 feet, and then your job is to lift the next 6, right? Because Joe can't make it, right? That was it, the first 4, that's done, right? So you go and you say, all right, so I need to lift the extra. If Joe lifted 4, then your integration starts at 4 because you are lifting 4 to 10. See that? That's kind of, so you can calculate the energy to lift the entire chain, but you can also calculate the energy, the work, to lift portion of the, right? So if someone lifted 4 feet and just left it there, right, on a nail or something, like bolt, then their integral would be 0 to 4 because that's how much they lifted, only 4 feet. Now, you come in and your job is to lift the rest. So then you will start at 4 feet and then you will go to 10 to lift the rest 6 feet to calculate the energy. Obviously, you will put much more effort than the person who lifted 4 because you lifted 6 feet, they lifted 4. And in addition to that, you were lifting heavier, right? Because you lifting after 4 has all extra chain added, right? So it's not that you just lifting more in terms of the length, you are also lifting heavier. So your work would be more than the work the person that only lifted, let's say 4, and you went all the way to 10. So this is your equation. And C and D is the amount we lift.
Screen.
What happened?
The screen.
Oh, thank you. So that's our formula to lift rope, chain. So whatever you are lifting, you know, partially, and then eventually you lift everything. Would something like this be important? Yeah. You lay cables underwater, and it's just like so much stuff that that gets to use this. So when you are designing motors that should turn those, you lift power lines between 2, right, towers, and it's just a lot of these kind of calculations to design machines that will do this for you, right? Because you're not going to do this by hand. The cable, electrical cable, is extremely heavy between the 2 towers. But you can just put, you know, any piece of equipment. Good. What's next? Pumping problems, love it. Okay, let's take a break and then have a part 2 for pumping problems, and these are really cool.